Okay, class. Hope everyone had a good weekend. A long homecoming week, I know for most of you. So today we are going to start the second important part of calculus, which is called the derivative section. Okay, we did first limits, and now we're going to go into the derivative, or also tangent line problems. Now, in order to do this section, I need to recap something we have done before in limits, okay? And you may just watch this part if you don't want to write notes, because I think we have wrote it before, okay? We have done this before. So I want you all to understand before we get into this very important concept in calculus in the derivative. Remember, at a time, I brought in a function like this, and we had a problem. We had a problem because we had a tangent line that was crossing one point. Remember, a tangent line, as a review, it's the point, a line that touches the graph just at one point. And at this point, we called it point P. Let me remember what we called it. X, f of x, right? I remember from that time we called it x f of x, where this point is x and where the y is f. Now the problem was that we needed an equation of a line, or we needed to find what line, describe this line, and the way we describe lines is with either slope-intercept form or point slope. But we couldn't do that because a tangent line by definition again means that it's touching the graph at one point, and to find the slope, to find the equation, I need 2 points. So what we did is we created this other point called Q, right? And we knew that Q was some distance away from x, and that distance we just called it delta x, distance of x. And therefore this point would become x plus delta x, right? So then this point would be x plus delta x for the x portion, and f at x plus delta x for the y portion, right? So we had those two in there. And then why did that point Q help? Because if I connected P and Q, oh, my line is really bad here, but I think you guys can see it. If I connect P and Q, I have what's called a secant line. A secant line, it's a line that touches the graph at 2 points. Now with 2 points, I'm successful at finding the slope. So in matters of Q, which is the secant line, we're going to find the slope of a secant line, S for secant, okay? And if we do that, we know that the slope is y2 minus y1 over x2 minus x1. And if we go further to use our good math notation, we know that the y2 point would be this one, right? Which is f x plus delta x. And then my y1 would be that one on P, which would be f at x. And then subtracting my x values, x2 would be x plus delta x, and then minus this one, which would be just x. Now, if I simplify my slope of the secant line, what I'm left with is with f x plus delta x minus f of x over delta x, because the x's cancel out. Now, this right here gives me the slope of the secant. This is what I have just explained to you here. It's nothing but algebra 1 with geometry. That's it. There's no calculus here, pretty much, okay? So this is what you have for the slope. But our main problem was to find the tangent line slope. So what we are going to do now that we're really good with limits, and what we had to do at the beginning, is this Q, we're going to try to move it closer and closer and closer to P. And now that we know the word limit, we are pretty much taking the limit as Q approaches P. And why is that? Hopefully now it makes a little more sense to you, because if I connect, I know it's hard to see here with my drawing, but if I connect P and Q together, this slope of this line and the slope as Q gets closer and closer to P, it's approximating the actual slope of P. The more I get closer to P, the closer the slope's line, the secant slope, is closer to the tangent slope. Now, I cannot be right at P, because if Q lands right on P, then I'm back to the main problem of how am I going to find the slope of a tangent line. But if I'm infinitely close, then that means I'm able to find the slope. Okay, so now what does that mean? How can I write that in what I just said in words? How can I write it as a math notation? So I can say as Q approaches P, infinitely approach, that means I want it to be very, very close. Then the slope of the secant line, it's also infinitely approaching the slope of the tangent line, right? And this is actually like a pre-calc kind of notation, but if I go now to limits, I would say that if Q is approaching P, this distance right here of X, it's getting closer and closer to 0. So in other words, I would write it this way. The limit as delta X approaches 0 of the slope of the secant line would equal eventually to the slope of the tangent line. This is what this means with limits, right? As I'm getting infinitely approach from Q to P, my slope of the secant is approaching the slope of the tangent line. But this is not a good formula. I'm just writing it so that you can know what we're doing here. What I'm going to do now is, hopefully you guys can write this. If you want to write this in your notes section, I would recommend this portion. What I'm going to do now is I'm going to erase this slope of the secant, and I'm going to plug it in with the slope of the secant we have from earlier, because that's the actual formula. That's why we had to do this on the side. So the limit as delta X, as the distance of X approaches 0, of the slope of the secant, which is f x plus delta X minus f of X over delta X, will give me always the slope of the tangent line at point X. Okay? So taking the limit of this function right here, which is the slope of the secant, will give me the slope of this tangent line accurately. All right, guys? So this is very important information. If anything in your notes you need to write is this piece right here. I'm going to erase it, so make sure that you pause it, write it down, however you want. But we're going to go off of that equation so that we understand it. Now, you might think, why are we doing all this when we know how to find the slope? I mean, we have done this kind of slope always in Algebra 1, in Algebra 2, in geometry, pre-calculus. Well, the problem is that if you remember, what is the actual definition of a slope? The actual definition of a slope means constant rate of change. Constant rate of change. And that happens just in a line, right? Because it's constantly changing per unit that it moves to the right. But now in calculus, slope has any kind of shape and graph, not necessarily a line, has a slope at that definite point. And that's why we need to learn this kind of formula. Okay, so let's go ahead and use it so that you can see how we can find that. By the way, sorry, I'm forgetting the most important part here. The slope of the tangent line at point X has a very special name for calculus, and that's called the derivative of the function f, in this case f, at x. So that word derivative that you have heard at the beginning and that you know that I told you is so important in calculus, all what derivative means is the slope of the tangent line at point x, okay? And of course, depending at what point that is, and slope of this tangent line that it's crossing. So make sure that you relate these two the same way. All what derivative means is slope. And if it's in a line, yes, we're talking about that constant rate of change. But when not in a line, when another kind of graph, then we can use this formula simply because that wouldn't be a constant rate of change. So then we're going to call it the derivative of f at x. Okay, let's start with giving you a graphical representation of a situation. All this that I just talked about, maybe it's going to make a little more sense to you if I draw it out. So you know how I just said, well, if we have, say, a line, right, and just so that you can get a little more better idea here, say I have this line and I know the point that crosses here is 2, oh, wrote it wrong. It's 4, 2, and this is the origin 0, 0. What is the slope of this line? Well, the slope of this line, you guys should be able to do that quickly. You would say, okay, it's rising 2, it's moving to the right 4 units, right? So it would be 2 over 4, which ends up 1/2. Well, that's easy. That means that this line has a constant rate of change, or a slope of a tangent line, or a derivative of 1/2. Because we know how to find the constant rate of change in a line. Is super simple. But what if now I bring this other graph right here, and I'm going to make a parabola. A facing down, doesn't matter, upwards or downwards, but I'm making a downward parabola. This is f of x, this is x. And now I ask you, well, I would like to know the slope, and I'm going to call this different points just so that we can have at A and say this is B. I want to know the slope at point A, and then it's going to sound weird. Finding the slope, if that's a constant rate of change, this parabola is not changing constantly. It's going up and then it's going down at different rate, right? Which is another word, by the way, of this situation, right? Of derivative. So it's going up and down at a different rate. So therefore, how am I going to find the slope of a tangent line? Well, now we call it derivative. Because if you make a tangent line right here, at this point of A, that function f has a slope just at that instantaneous moment. Okay, so that's why at A we would find its slope of a tangent line. However, and definitely we would expect this to be positive, some positive number because it looks like a line. However, if I ask you to find the slope of the tangent line or the derivative, let's change the calculus term better, right? Or the derivative of the function at point B, of the function f of x, then your answer is not going to be the same. Notice, this is going to be a negative slope. And even if I ask you for another slope right here, it's still going to be negative, but steeper. So notice that the derivative of the function in a curve other than a line changes with respect to x. And that change we call derivative. While here, no matter where I ask you for the slope, your answer should always be 1/2. Changing to calculus term. What's the derivative in this point? At this point, at this point, it's always 1/2. But the derivative in this curve will always be changing. Okay? Oh, let me bring this question right here to see if you guys can understand this. What if I go to the maximum point and I take a tangent line right there? What would be the slope at this point C? What would be the derivative of this graph at point C? Hopefully everybody's telling me the derivative at this point C, it's 0, right? Because at this point, it's having no change of rate. So that would be 0. So hopefully graphically, now it makes a little more sense. Now let's get into the algebra kind of how are we going to find this when we have our formula, okay? So example number 1. Find the slope of the function using the definition, or find the derivative, I mean the slope of the tangent line. Find the slope of the tangent line, and we are here introducing also the word derivative, so we can call it like that too, right? Find the derivative of the function f of x equals to 3x plus 1 at the point, notice when we find a derivative, we always want a point, at the point 1, 4, when the derivative is at a point. Now, without any calculus, say it in your heads, in your minds. What is the derivative of this? Hopefully everybody's saying, okay, we definitely know that it's 3 no matter where. Okay, I do know that because you guys know this is y equals mx plus b. But I want you to use the definition of derivative that we have just done at the beginning of the lesson. So in other words, I want you to use this. The limit of f of x plus delta x minus f of x over delta x as delta x approaches 0, because that's what we use. We use the secant line slope, we approximated its distance to 0 to p, and then that gave us that slope of the tangent line, or the derivative. So we're going to use this just to prove to you that even taking this long way, the answer is going to be 3. But remember, in all our examples, line is not going to be the only thing you're going to deal with. You're going to deal with different kinds, so you really need to know how to do this, okay? So the first step you want to do, this is going to use a lot of composition function. And if you notice, you have done examples like this already without knowing you were actually finding the derivative. Number 1, it's I want to find what f of x plus delta x is. Well, I have a function. If I have this inner part, I'm going to plug it in for any x I see here, and I get 3x plus delta x plus 1. Okay, now let's go ahead and solve this. This becomes 3x plus 3 delta x plus 1. All right, number 2, we already have f of x. F of x is simply, right, and all what we're doing, guys, is we're trying to get this piece right there, this piece right here, and then this becomes 3x plus 1. Now that that's done, all I'm going to do is plug it into my formula right there, okay? So my formula calls for the limit as delta x approaches 0 of this whole thing, which is 3x plus 3 delta x plus 1 minus, be very careful. This messes up a lot of students because you have a minus in there and then we don't distribute. So what I like to do is I like to open parentheses so that I know and I'm aware that that's going to distribute into the expression right there. And all this over delta x. Now, if you look ahead, you know that the negative is going to go into the 3x, so that's going to make negative, and for the plus 1, we'll also make it a negative, right? And if I have to clean this up, and I hope everybody's going to be able to see this. So if I have to clean this up, this will become the limit as delta x approaches 0 of 1 goes with negative 1, 3x goes with minus 3x, and I'm left with 3 delta x over delta x. This is a limit problem that we just know how to solve. Well, if it's delta x over delta x, can I cross them out? Yes, because they do not equal to 0. They're approaching 0. So what I'm going to do is I'm just going to cross it out. And my final answer is 3, which I already knew from my just algebra skills. So the slope at 0.14, it's 3. And if I would have said what's the slope at 0.2 when x equals to 2, it would also be 3 because I don't have no x to find out. Okay, so that was the first example, simple, using a line. Let's go ahead and use another one without a line, okay? Let's do one more example and then you guys can start working. I think you guys, because of the time of the class, you might have to do classwork, homework together. Okay, now this other one would be the following. Would be x squared plus 3x at point 2, 10. I said 10, I wrote 0. Okay, 2, 10. And that's because if notice x equals to 2, and that's 2 times 2, 4, plus 2 times 3, 6, and that's why this is x equals to 2y. So what kind of function do we have here? Here we have a parabola, right? And I'm going to draw it later after we find the actual number so that it can make sense to you. But remember, if I'm trying to find the slope of the tangent line at this point, that means that in the parabola, which is just really quick, I don't know where is this parabola at right now because I didn't look, so it might not be accurate, but I know it's upward. Okay, so if I have an upward parabola, and I'm not going to use a grid, I'm just going to use a parabola like this. And I know I'm at 0.2, wherever 0.2 might be. What is going to happen is I'm going to make a tangent line, and I'm finding that slope of that tangent line at this given point because it will be different everywhere else. So what I'm going to do is I need to find the slope or the derivative with that long formula we have, which again, we're going to have to write it here. Limit of delta x of fx plus delta x minus f of x over delta x, okay? All right, so now let's do step number 1. Let's go ahead and find our fx plus delta x according to this function. I plug in x for every x I see here, and I get x plus delta x squared plus 3x plus delta x. And possibly you're starting to see that the algebra here is going to be heavy because if we have squared or cube, you're going to have to actually expand that. So if I expand it, I'm going to use my FOIL methods. Please do not just say x squared, delta x squared. That's wrong. You have to FOIL it. And we know we have x times x, x squared. We would multiply x plus delta x twice. So we get 2x delta x. If you do not understand this step, you should be foiling this separately and pausing the video. And then plus delta x squared. That's the expansion of this piece right here. And then finally, I'm going to just distribute this, which will be 3x plus 3 delta x. That is just this piece. Now, my second piece is just going to be f of x, which is that f of x equals 2x squared plus 3x. Since I already have everything set up, now it's time to find this. And what I'm going to do is I'm going to write it because it's going to be long. So I'm going to write it like over here. My x plus delta x is this whole thing, which would be x squared plus 2x delta x plus delta x squared plus 3x plus 3 delta x. Okay, let me check because you guys are going to find my mistakes. I've been giving a lot of extra credit recently. So x squared, 2x, delta x squared, plus 3x, 3 delta x, minus. Again, you want to use parentheses just in case you don't want to mess up all this algebra you did, hard work, with any sign mistake. So x goes into x squared, making it negative, and then it makes the other one negative as well. And this is what I have, all over delta x. Now it's time to do some simplifying. Okay, continuing with the lesson, I had to make a quick stop because something happened to my battery for my recording here. So anyway, we had simplified this. So not simplify, we had we rewrote everything, and now it's time to simplify. So it's the same problem, guys. It's just I had to just quickly stop. So here we have x squared goes into x squared, or cancels each other out. Then 3x cancels with that. And then if you notice, our final limit or simplified function here after we did all this work would be 2x delta x plus delta x squared plus 3 delta x. Oh, and I'm forgetting something very important on both of these. I got to use my limit notation always, because we are taking the limit on each of these simplified versions still until we don't plug in the 0, as you know, with limits. Then we can't say we finished taking the limit. So limit of 2x plus 2x delta x plus delta x squared plus 3 delta x all over delta x. Now, as you know, with examples that we just had on our test and prior, to take the limit, you simply plug in the 0, and you're going to get 0 over 0 in determinate form. So I got to use my algebra. And one way to solve this would be to take out a delta x from both. Well, here it's already factored, but on top, I can take a delta x from every single term that I have. So I would have delta x plus 3, okay, taking a delta x from each one of them. And then in the denominator, I would end up with with delta x. And I would be able to cancel, given that delta x does not equal to 0, but is simply approaching 0. And my final answer here would be, if you plug in delta x equal to 0, the derivative, which is what we're finding, find the slope of the tangent line or the derivative of f. The derivative of f would simply be 2x plus 3, since delta x went to 0, right? So now it's something different for you guys. You have found the slope of a tangent line or the derivative, and as you did this, you didn't get a value, you got a function. Is that okay to get? Yes, it is. So from now on, since you're finding the slope of a tangent line, every time you find the derivative, you're going to get a function if it's not a line. When it's a line, like the example that we just did before, you're going to get a simple number. But now the derivative function of this function right here, f, it's 2x plus 3. Since the problem was to find the derivative at point 2, now we're ready to plug in 2. So if we need to find the derivative at 2, 10, then you would say, well, 2 times 2 plus 3 will give us 7. So the derivative of the parabola x squared plus 3x at point 2, it's 7. But the derivative function is 2x plus 3. So what if I change this function and I say, well, I would like to know what is the derivative of this function at the origin, 0, 0, because if you plug in 0, your y would also be 0. Then your answer here would be 2 times 0, 0, plus 3, 3. So for something that goes through the origin in this case, it would be only 3. So what I'm trying to tell you here to wrap up everything, guys, is that the derivative or the slope of a tangent line will always give you an expression if it's not a line. But would ever give you a value? Yes, if you're finding the derivative at a specific point. This is algebraically. Let me go ahead and erase this so I can show you with a graph what we just did and how this should make some sense to you. Okay, so let me go ahead and quickly erase. And we already found the derivative. I'm just going to write it right here. It's the derivative was 2x plus 3. And I'm sorry, my pens are just really bad. Let me see. This is 2x plus 3, just to keep it here, okay? The derivative is that. If I were to graph this parabola, I'm not going to be wasting too much time on doing it, x-intercept, y-intercept. You guys should be able to find out how to graph this parabola. But if we were to graph it right now, this parabola, it's crossing the origin like this, okay? And it goes this way. It's an upward parabola. It's exactly like this. The point 2, of course, is on this side, which eventually we were finding the derivative at 210, right? So if I put point 2 right here, and I make a tangent line right there, you guys know that the slope of that point is going to be positive. And we just found out that it's actually 7 on the slope of the tangent line. But if my question earlier said, well, find it at 0, remember? I also said, how about if you find it at 0? Well, at 0, it's also positive, but less positive because the tangent line is not as steep. And when we plugged in 0 on this function, then the slope of the tangent line just gave me 3, right? And if I were to find it, and let me just test you guys and see if you understand this. Say I would have -5, and I know my tangent line is right here. Well, what would be the slope of this function, tangent line, or the derivative? Let me change calculus term. What is the derivative of this function at point -5? Then what you do is you need to find the derivative function, as we did, plug in the -5 in here. -5 times 2, -10 plus 3 is -7. And it makes sense that it's -7 because it's a negative slope, right? If you notice. So, okay. So we found what the derivative means. So again, to wrap up, derivative, when it's not a line, will give you a function. So if you're only asked to find the derivative of the function, that's it. But if you're asked to find the derivative of the function at a point, then you got to find the value, because all you got to do is plug in the point. So let me get my eraser. The 2 questions we did today was, this is our second question. It was x squared plus 3x, and the first question was f of x equals 3x plus 1, right? When asked what is the derivative, this is just the end already, derivative of 3x plus 1, your answer should be 3, no matter what, because it's a line, so it's going to be a value. So if I find the derivative of 3x plus 1 is 3, how about the derivative of 3x plus 1 at point x, or at point, no, at x equals to 1? The answer would still be 3, because it's a line and it always have a constant rate of change. Now, if I were to ask what is the derivative of x squared plus 3x, then your answer should be the derivative is 2x plus 3. That's it. But if the question asks what is the derivative or the slope of the tangent line at point 2, at x equals to 2, now this would end up being the derivative at point x equals to 2 would end up being 2 times 2 plus 3, which is 7. Okay, guys? So hopefully you understood this lesson. What you're going to do today is a quick worksheet on 4 questions that you need to show by the end of the day. Finding the derivative of the function. I don't want you to plug in any points. I want you to do exactly what we did here, even if the worksheet doesn't necessarily tell you to do it that way. And at the end, all we want to see, Mr. CEO and I, it's the derivative of the function, which might come in as a function if it's not a line. Okay? Have a good day.